Welcome back to the second talk of the afternoon. It's my pleasure to introduce our own Eduardo Silva, talking about dead ends on wreath products and lamplighters.
Okay, so thank you very much for inviting me. So today I would like to speak about properties of calligraphs. Mainly we want to understand when can the elastics of calligraph be extended to larger ones, or more generally how to connect a sphere of radius r with a sphere of radius r plus 1. So just to fix with the phonetic generated group. We will fix generating sets, so it will be generated by S finite. We can take S to be symmetric, it doesn't matter because we will be working with the word length. So, word length. So implicitly S will be symmetric. Just to fix notation, the word length of an element G, which is the minimum number of generators you need in order to express that element in that generating set, right? So T equals to S1 up to Sn, Si, S S minus 1. So as I was saying, with this, this gives a metric of your group, right? Imagine that your group is partitioned on spheres. One tends to think that since groups are very symmetric, this should look something like clean space, hyperbolic space, or something. But it's not always like that, which leads us to the following definition, which I will explain more detail. Which is that of, I will define for groups, but in general, a metric space of unbounded depth. So we will say that the space GS has unbounded depth. For any positive integer, there exists an element on the group that's that. For any word of length at most n, for any generators S1 to Sn, let's say in S meaning S minus 1, and also using the identity, so that it's a word of length at most n, we have that the word length of G multiplied by this word is not larger than the word length of G. So what are we saying here? We're saying that, again, looking at spheres, so these are elements of S, or they are larger. We're saying that if we're here in G, if we want to reach the next sphere, we need to multiply by at least n elements before reaching that sphere. So one should think of this property as being somewhat pathological, and it's a bit difficult to imagine it also when you think about balls as being complex sets. So we will see some examples.
Could you please explain one more time the picture?
Yes. So I'm saying here that T is in a sphere in this metric space. So it's word length. This is a sphere of elements that are at word length of T from the identity. And I'm saying that in order to reach the sphere of radius word length of T plus 1, you need to multiply by at least n plus 1 generators. So you need to do a path, the distance between this sphere and the next one, starting from G, is at least n plus 1. Does it make sense? No?
Wait, do you want to say S plus the length plus 1?
No. Here I'm saying that
Okay.
when you multiply by any word of length n, you do not increase your word length. So in order to increase your word length, you need to multiply by at least n plus 1.
Okay.
Or more, possibly. So which groups have this property, which is the trivial example? Finite groups, right? A finite group, if you choose an element that maximizes your word length, of course it's going to have the property. So a very boring example or a remark. Finite groups always have this property. I will say UD for unbounded. This may seem a bit weird because many groups one thinks of do not have this property. So we'll state a proposition where I will tell you about many families of groups that do not have this property. So let's say that the following infinite groups have to work with infinite groups, otherwise they have a moment there. I will say do not have a mounted depth. I will say they have uniformly of the depth. For every generating set. So the first example or the first family is abelian groups. So any abelian group you take, you are always going to, once you fix generating set, if you look at the neighborhood of some large fixed radius, you're going to be able to intersect the larger sphere. So this is due to Tunich in 07, 08, and due to Denner in 09. So Tunich proved the case of Z, and Denner proved the more general case. Also, it's true for virtually abelian groups. So virtually means that you have a finite index abelian group, subgroup.
So this is not a QI.
No, it's not a QI invariant. I will get to that after this proposition, but in general, no. It's not invariant under even a change of generating sets.
No.
So for these families of groups, it's invariant for different generating sets, but in general, it will not be. So virtually abelian, this is due to Warshall. So I will comment a bit on that when I finish this proposition. So this is maybe I will continue here. Also for hyperbolic. So if your group is hyperbolic, again, in a large enough neighborhood, you will intersect a larger sphere. This is for Wolfskin. 97. And it's also true if your group has at least two ends. So any group with infinitely many ends, or well, virtually Z, is also has uniformly bounded depth. So this is.
Can I have one more question? I mean,
Yes, of course.
I feel like I don't maybe still understand the definition because it seems to me for Z like obvious that you can do it, but it's probably not one.
Yeah. So what's not okay? So the thing is that let's do a little example. What happens if you take Z, the integers, with the generating set 1? It's true that you do it like the Killing graph is aligned and always increase your world map. But for example, if you take the generating set, which is 2 and 3, then you can see that the element 1, you can write it as 3 minus 2, right? So its world length is 2. But all of its neighbors also will have world length at most 2. Okay, because its neighbors will be 1 plus 3, which is 4, which is 2 plus 2. 1 plus 2, which is 3, which is world length 1. So in fact, here 1 does not have neighbors in the next sphere. However, this proposition tells us that if you look at a larger sphere, you will at a larger neighborhood 1, you will intersect the next sphere.
So if I would take the standard generator, it is obvious, right?
Yes, of course. At standard generators here, or ZD, or in the free group, anything. Yeah. So again, I mentioned this property is somewhat pathological because you do not imagine that it happens very often.
So it's interesting that abelian came 10 years after hyperbolic. Is
Yes.
is it much harder in abelian group?
No.
Well,
I mean, I think it's it's related to like who was interested in understanding these properties, somewhat a bit specific. Well, maybe it's well. I also comment a bit on the proofs, but you would say that abelian is easier. The thing is that here Bogopolsky came to these things because he was not interested on this property. He was interested in proving some conjecture about quasi-isometries and commensurability between hyperbolic groups. And his proof he did an algorithm on the group, basically a procedure, an inductive procedure, where he needed to go from the sphere of radius r to the sphere of radius r+1. So he was forced to prove that if you look at an R2 neighborhood, you will intersect the next sphere. So he was, in some way, it was a consequence of what he was trying to prove, that he was forced to understand that hyperbolic groups do not have this pathological property. Any more questions? We will get used to it. So as I was saying, this is for this group, it's invariant for every generating set, but in general, it's not. So maybe a remark. Having a moment that is not invariant under a change in generating set. But however, it will be an invariant under what people call rough isometries, which is another name for 1C quasi-isometries. So a quasi-isometry where your multiplicative constant is 1 and you only admit additive error. Or invariant under so this is maybe one way of proving the abelian case. If you look at the asymptotic cone of an abelian group, you get Rn with some metric that comes from a norm defined by the generating set you started with. And then when you are in the Euclidean space Rn, you can show that you can quickly find geodesic rays to infinity. And it turns out that by a result of Drago, those two metrics, the metric of the asymptotic cone with the group, are at bounded distance from each other. And so proving it for the asymptotic cone implies the case for an abelian group. Okay. So now we should speak about infinite examples of groups that have this property. So I will mention the example and I will explain it a bit afterwards. So this is the first example of an infinite group that has this property. It's due to Cleary and Tabak, year of 4. And they say that fix or consider any group A with a generating set SA, which has a bounded depth already. So a finite group, for example, that has. I take a group with 2 elements. That's the simplest example, and it's not trivial, of course. Then the lamplighter group A with Z, where this will be the lamp group and this will be the base group. We'll explain that in more detail afterwards. Has unbounded depth with respect to the generating set of the union of this one with the generating set of Z. So let's say union 1. So these were the first examples. The idea, which we will exploit later, is that you can express this work metric here in terms of a combinatorial problem in the KV graph of your base group. That problem will be deterministic problem. And well, we will see that. But before, I would like to mention a couple of other things. So, I would like to mention that, well, that was the first example, but it's not true that that group has this property for every generating set. So,
what do you mean by first example? First example of what?
First one example of a group, of an infinite group that has a bounded set. Because the other ones are uniformly bounded, right? Yep. So it's a natural question to ask whether there are groups that have the property for every generating set. That is not one of those. So this is a result of Warshall. It tells us that the Heisenberg group, the discrete Heisenberg group, has this property. So the Heisenberg group H3 of Z has unbounded depth for every generating set. So I will not explain this in detail because it's not the object of the talk, but this is related to the fact that the central subgroup is quadratically distorted in all directions in some way. And a way of proving this result, again, is using the invariance in the 1C quasi-isometries. Again, going to the asymptotic cone, where would be the real isomer group with a what's called a Carnot-Gradilori metric. And well, there you can use again tools of how you understand that Riemannian manifold to prove things about this metric. But this is, as far as I know, the only example of an infinite group that has this property for every generating set. And so I will also like question like, why do we care about these things? Some motivation. Yeah, we're studying geodesics on groups. That's cool. But why? Why would it be interesting to know if your K graph has this property or not? So well, the first one I already answered a bit. So Bogoboski, for example, was doing an algorithm on a hyperbolic group, and he needed to know this information for his procedure to work, for his proof to be true. So you encounter these things when you're cycling geometry with your geodesics or your work metric kind of things. But I will try to illustrate this with some things that measure how regular your K graph is, how good or how bad it is. So you tend to think that this property implies that your K graph is not very regular. So the first one is a proposition due to Warshall also, which tells us that if you have unbounded depth, then it's not possible to find a regular language of geodesics for your metric. So there does not exist a regular language of geodesic words. Right, so if you want to codify in a computer the metric of your group, you'll have a hard time maybe. Regular means that it's read by a set of automata.
What do you mean by regular?
That it's a language on the alphabet S in S-1 that's accepted by a finite state automaton. So a Turing machine. Okay. Yeah, I mean, yeah, automatic or weakly automatic, because if there's like not representatives, not the complete language of geodesics, just you cannot even take representatives that. Yeah, but automatic, it's a good word. And another thing, a more recent theorem from this year of Bernoulli and Baudard. Which tells us something similar in some way, that if your group has unbounded depth, then your complete growth series is not what's called NG ratio. So what does this mean? What's the complete growth series of a group? So it's a power series, right? So gamma of a variable x. As any power series is sum of some positive things, coefficients next to the n. And the complete means that we are summing over all elements in the sphere of radius n. G. So this is power series with coefficients in the group semi-ring NG. So the numerical growth series would be to put here the size of the sphere, so just integer. Now we're putting a complete growth series, so we're working in the group ring here. So saying that the complete growth series is not NG-rational means that basically these coefficients here, this list of elements in the sphere, do not satisfy any linear recurrence relation between them. So yeah, I think these two things give examples of how irregular your K graph is. So are there any questions? Okay. So I would like to pass to the main thing of this talk, which are great products, to really understand clientelar's example and see how it works in more general cases. So just very quickly, we'll define what the weak product of two groups is. In our notation, it will be the direct sum of copies of A indexed by B, similar product with B. So here B, conjugation by B means translation on the direct sum. And if we have generating sets of each of these groups, S8 and SP, generating sets, then their union, seen inside of this group, is a generating set of the grid product. Well, here we are identifying B with the copy of this coordinate of B, and we are identifying A with the copy of the origin of the identity of B. So this is what we call a standard generating set of the grid product. We imagine, we call these type of groups also lamplighter groups, because we imagine that an element here, so X, you imagine that you have your group B here, that at each element you have lamps, and each lamp can be in a different state according to the group A. A is called group, and B is called the base group. And so this function f tells you what the configuration of lamps is. So this will be f of B. And this point x tells you some position inside of your group where you imagine there's a person called the lamplighter person. So the dynamics in this group is that when you multiply by elements of B or generators of B, this person moves throughout the group B. Well, when you multiply by generators of A, you change the lamp state in that position, in the position that person is standing on. So with this interpretation, you can get a formula for your work metric. So say this is a proposition. It was first noted by Barry in the year 92 when studying growth series of grid products. And there's like a formula for your word length in terms of these generators. So what's the word length of an element fx? First, of course, you need generators to light each lamp to its corresponding state. So you need something like the sum over all positions, the value of f at the position. So of course this sum is finite because f is finitely supported. And however, you need to do more things, right? Because this person can only light things at its current position. So they need to travel from the identity. They have to visit all of the lamps that are at some non-trivial state and finish at this point x. So we call that, we know that by TS EB x support of f, meaning that, again, this is important, that's why I repeat it. It's a path of minimal length that begins at the identity, finishes at x, and visits all of these finite sets, the support of f, inside of the K graph of B. So this depends on the genetic set of SP. Great, so having that, pre-interact example is true. So let me show you how you construct an element that has large S. So let's say that we're working on Z over 2Z with Z. And again, cyclic generator, so 1 modulo 2 and 1. So this will be SA and SB. So we're going to take G to be lighting all lamps between -n and N. So we will light all lamps here. And we will place the lamplighter person at the origin. So what's the word length of this element? Well, we will have the lamp part, and the other part will be given by the path this person takes from the identity to visit all these and finish again at the identity. So, well, we're in a line, there are not many paths, right? So it's easy to see that the optimal way, or the only thing that they can do, is to first go to one extreme, then go to the other extreme, and then come back to the origin, right? That's the optimal thing. But if we now start multiplying by, let's say, n generators or something, what's going to happen? We're either going to be turning off lamps, right? Because all lamps are turned on, so we might as well turn them off only or leave them as they are. Or we're going to change the position of this lamplighter person. So any configuration will be something like 0 minus n, some lamps will have been turned off, and maybe now the person is standing here. So turning off lamps is good for us, right? Because we're going to reduce our word length. That's what we want to show. We want to show that word length was going to increase. So turning off lamps, good. And the other part is that we need to see that the length of the solution to the traveling salesman problem, so the path this person has to take in the graph here, also decreased. And that is the case because now the optimal solution is doing something like this. You first go to the other extreme you're not in, and then to the extreme you're in, and you stop before going to the origin. So now you're saving all of this space also in your solution. And so, well, this drawing is basically the main idea behind the result of linear antibiotic, which tells you that this group actually gives you an infinite example of group with among the dead. So the thing is that we would like to understand this type of examples in more detail. But we want to understand how the properties imply that you have for some that in case of Hudson group, some all generating sets with amount effect. So understanding the family of wreath products is important because it tells you which things are preserved or which things are not preserved. So it helps you see how different families relate to this property. So this is a property of Z, this is a property of wreath products, etc.
Sorry, I have a question. So you said that from this group, if you take another generating set,
Yes.
it's not.
There are other generating sets different from this one,
Yeah, such
for which you do not have this property. So those generating sets, I don't think I have time to explain them, but basically they are not very intuitive thing, but you do a lot of jumps for, like, you can do jumps of 4 and 4,
Okay.
and you start like losing, like, you can always locally modify your work. Maybe we can discuss that in more detail if you're interested. But in the case of the Heisenberg group, it's not possible. All generating sets have the property. So how does this generalize quickly? So first, Kilian Tabank's example replaced this actually for any. That's, if you think about it, that's actually a very necessary condition, right? So you always need to work with a lamp group of amount depth for this type of generator, standard generators. Right? Because otherwise you simply don't care about the wreath product structure. You just start multiplying your lamp coordinates, and you will increase your rolling. So this is a necessary part. But what about the base group? What can you do here? So it's also very quick to see that you can take BSB to be any free group with the free generating set. And the same argument more or less will apply. You will also have this property that the worst thing you can do is to go to all extremes, to all branches, and then go back to the middle. That's the worst thing around tree. So these are more or less the same group. But once you start getting out of that, it's not clear what happens, right? For example, very simple question. What happens if you are in Z squared? So now you have a lamplighter that moves on a plane. Do you still have this property? So in that case, in a difference with when you're moving on a tree, there's not many hopes to get explicit solutions here, right? Because well, this is a result of Kalampovich and Mogadam that finding the length of an element in a wreath product when the base group is Z squared will be NP-hard, right? Because the traveling salesman problem is NP-hard there. So you cannot have explicit formulas in contrast with the explicit formulas you can get for trees. So it's not clear. And even it's not that clear what happens if you take Z with other generators. So now instead of taking the second generator of Z, you start moving with, like before, like 2 or 3. The solutions to the traveling salesman problem are going to be very different. So this is very sensitive to the generating set you choose on your base group. Okay, so I hope I motivated forward enough so that now I can introduce what I managed to understand over the past few months. So Again, let's fix a group like this. So fix our round group. I will think of a finite group. Same. First result tells us that for any group, finite generated group, there exists at least one generated set which does this. And in fact, infinitely many, such that A with B is has a number, right? So you can always find at least one appropriate Cayley graph for your base group, which works. And moreover, in the case of abelian groups, any generating set works. So if this abelian, I will just write like this. ESP works. Okay. So I would like to comment a bit on how we prove this, because it's the same idea, but very different to what we did with client for example. Why it's different? Why it cannot be the same? Because now we will not be moving on a tree if we are in such Z where we have many cycles. So this behavior here is not going to happen. It's impossible to hope for that to happen. So we're actually going to go to the other extreme. We're going to go to the extreme where your solutions to the traveling salesman problem are in fact very good, meaning that your Cayley graph is very connected. So what's the idea? The idea is that we want to mimic what worked here. So the naive thing would be to take your group B, look at the identity and a big ball around it, and light all lamps there, and place your lamplighter person at the origin. That would be a naive candidate for an element that has arbitrarily large depth, like trying to exactly mimic what happened there. So in general, this will not work, but we will construct a generating set so that it works. So we find SB that let's say the following quotes. The following holds means that there exists a constant M and some family of finite subsets of SB, which will be more or less these balls. So there exists a family F of finite subsets of B, such that first, this family contains balls. So for any positive integer, there exists an element here such that the ball center at the identity and the radius n contained in F. So there are sets that are balls, but maybe a bit larger or with other elements. And why would I want that? Because I want the second property, which is it's that these elements have good solutions to the traveling salesman problem, meaning that for any F in this family and elements in F, the solution of starting at the identity, finishing at X, and visiting all of F, this needs to have at least, of course, the cardinal of F, right? Because we have to visit each other. But we want it to be not that much larger. We want it to be the same up to an additive error, which is uniform for all the family. So what we're saying here is that we want to construct subsets, arbitrary large subset that contain arbitrary large balls around the identity, which are, we say, we use this terminology, quasi-Hamiltonian, because a Hamiltonian path will be one that visits its vertex once. So we are allowing some repetition, but a uniform amount of repetition among all sets. And by the same reason that this property was invariant under 1C quasi-isometries, this will be enough to guarantee that your elements imply the existence of elements of arbitrarily large depth. So I think you can imagine how this implies that this idea works, right? Because again, when you start multiplying by generators here, you're either going to turn off lamps, which is good, or you're changing the final position of this person. But this tells you that that does not change that much the word metric. Okay, so how do we find these SVs? Vertices lemma. So in some way we want K graphs with high connectivity properties. So this is a general fact. So if you, for any infinite B, for any generating set, let's say SV tilde, you consider, we will define a new generating set, which will be SV equal to SV tilde union SV tilde squared union SV tilde cube. So what we're saying that you start with any Kelly graph of your group, and we are connecting vertices that are a distance 2 and also a distance 3 from each other. We're adding those edges. And turns out that that is enough to guarantee that you will have very strong connectedness properties in your graph, which particularly applies this property with n equals to 1 or 2, 2 I think. And in the case of abelian groups, so this together with the above already implies the first part, right? And in the case of abelian groups, we're saying any generating set works. So not any generating set is like this. So we need to say another thing. So if B is abelian infinite, and also we will fix a generating set, but we will suppose that it's different from the most basic one. It's different from Z with 1. So it's not a line, it's not a tree. So it has cycles. Then, well, we have two cases. The first one is that if this group is virtually Z, so if the free run of B is 1, then actually, as graphs, we are able to embed Z, finite many copies of Z, at least 2 of them, into your K graph in a bijective way. So let's say that this is a bijective, and we preserve edges, so it's 1 digits. Many of matrix spaces. And so by this I mean the graph, literally this graph. Okay. And again, it turns out these graphs have this property. These are what people call wreath graphs. Since this embed bijectively into the K graph, this K graph also have the property. And in the case of higher free rank, it's the same, but with a lattice Z squared. So if rank of P is bigger or equal than 2, then the same but with lattice. So it's also to K graph. Great. And now this, well, here I have made here, great. There is a very natural question that arises when you look at this theorem, right? So we say for any infinite group, you can always find a generating set that works, infinitely many, but not all of them necessarily work with this technique. But for abelian, every generating set works. So it's natural to wonder whether we really need to write abelian here. Does every generating set always work in order to give rise to a lamplighter group which has bounded depth? The answer is no, it's not possible. So this will be our last thing we'll speak about, which are a family of examples where this does not have a bounded depth, it has uniformly bounded depth. So the case of Figurante line is not general in the sense that you can use any this example of base groups, which will be virtually free, will be free products of finite groups. So we'll fix H and K to finite groups. We will fix generating sets for these finite groups. And we will say, let's say the group or the pair A, wreath, H, K, A, union, SH, union, SK. So this is the standard generating set we always talk about. We'll have uniformly mounted set, so not the property. If and only we have some geometrical condition on the solution to the topic problem that is finite graphs. So only on this finite information here, which I will grade it and then explain it. So this constant will be a constant of the Cayley graph, which is called the Hamiltonian difference for us. So h of h plus h of k plus k is here equal to 1. Okay, so what is this constant I introduced? It measures how different are solutions to the Trolley-Sesma problem, which are cycles compared to those that are not cycles. So cycles versus paths. So here, let's say for G, let's see a finite group. We have that h of G SG is equal to the largest solution you can get when you are not. So we take G different from the identity, and solution starting at the identity, finishing at T, and this is in all of the group, minus your cyclic solution. So e.g. So you're seeing how different paths that visit all of the group are from cycles that visit all of the group. So I'll illustrate this with an example and explain the intuition behind this result. So this is the case where it works. Is when we take H to be a group for the and when we take K to be a group, cyclic group of order 8. So we'll see why this is important. It's the smallest value that works for 2. So maybe let's compute this number for this case. We'll take a second, right? So what's this number here? So the Cayley graph page is just an edge, right? So when you're not a cycle, your solution has 1, right? You just do this. But on that table, you need to have 2, so you also come back. So it's minus 1. On the other hand, what happens in the case of here? So 8, okay, let's say. So here is that maybe I'll draw it here. How does this Cayley graph look? It's an octagon, right? So we have something like this. Let's see that here's the identity. So of course the cyclic solution will be going through a cycle. That's not a surprise. So this will be minus 8. But the non-cyclic solution, the last one, will be finishing at the opposite element of the identity. So here. While here, the solution that visits all vertices and finishes there will stop here, and then it needs to come back to G. So it does something like this. So it has for length that is 7, 8, 10. And magically minus 1 is 1, right? So it's a small slide. And in these groups, we have uniformly bounded set. The thing is that when looking at the graph of the free products, right, it's free products of copies of this graph with this graph. And this property here implies that changing the final position of your lamplighter person in a local neighborhood, in a neighborhood of where you're standing at the current moment, you can force this, the Travis-Sesma problem to change a cycle into a path like this. And once you do that, you will have increased your problem with only a bounded number of movements. So you just need to go from one element to maybe the next one or the next one, depending on some borderline cases. And the difference in your word length you get is precisely this difference. And if it's at least one, it's because you are increasing your word length. So you are not about of a bounded set. So yeah, we'll stop there. Thank you very much.
Question?
What about the Heisenberg? So like, what's stopping people from generalizing the Heisenberg group to like photons?
Yeah,
I mean, is that
so
expected or?
there are many problems. I mean, we're trying to work on generalizing it, but it's not that quick. So maybe I can write something here. So the thing is that first, it's very sensitive under very basic group operations. So let's say that you have a group G which has unbounded depth. Then let's say that maybe it's a Heisenberg group. So it has bounded depth for every generating set. So for every. Then a group G times Z will always have at least one generating set with a bounded depth and another one without. So the operation of taking direct products breaks this property immediately. So it's not possible, for example, to generalize it to all nilpotent, non-mutually evident groups. The second thing is that, well, it's also not true in general for two-state nilpotent groups. So if you take, like, for example, higher dimensional versions of the Heisenberg group, where you have more generators but still a cyclic center and you're still two-state nilpotent, you have generating sets that do not have this property, because basically in the Heisenberg group, it's similar in the sense that you reduce your word metric to understanding a combinatorial problem. And in the Heisenberg group, your combinatorial problem is to get an isoperimetric inequality, right? To have some area. This area will be your Z to the N, right? Your center element. And you want the word metric is given by minimizing the perimeter of a curve that encloses area N. So when you have multiple generators, you have to break this square into many squares, and that's not optimal. So you increase your problem. So it's not, what I'm saying is that it's very delicate thing to study.
Is this the only finite group where you get a negative H? The Z1, 2?
No, I mean, no, so I think that if your group is of odd cardinality, or no, even even cardinality, and if your KD graph is Hamiltonian connected, then you're always going to get this. So Hamiltonian connected means that there's a Hamiltonian path that connects any two vertices. So maybe that's also interesting to comment that actually in most cases of finite groups you can imagine, or finite KD graphs you can imagine, you're mostly always going to get less than or equal than 0 in this sum. Because most of those KD graphs will have strong connectedness properties. So cycles here are very exceptional in the sense that they are not very Hamiltonian connected, because they have these, they're not Hamiltonian connected. There are no paths that visit each vertex once and finishes wherever you want to. And I would guess that basically these are definitely the only examples among abelian groups. But among all finite groups, it's unknown. It's an open question related to Lovat's conjecture. Lovat's conjecture asks whether every finite KD graph admits a Hamiltonian cycle. So that's not known. So it's related to those problems on finite KD graphs.
What's next?
What's next? The Heisenberg group. Yeah, important groups. Yeah. Or also. Well, this is known also for all the generating sets of real products. You get what are called distal leader graphs, which are for spheric products of trees. So you fix a boundary at infinity, you get level sets, and you take a subset of the products. So that's true there. Well, there are things you can do in that direction also.
Great. Other questions in the room?
It seems to me that, I mean, having found the dead end implies this property, this unbounded.
What's the first property you said? Having bounded?
the dead end.
What does that mean for you?
I mean, just because you mentioned the work of Leonard,
Yes.
and it seems to me that in that work, I don't know if.
Yeah, I mean that's I mean
That they proved that, I mean, he proved that building groups have bounded dead end.
how a finite number of dead ends.
Yeah.
Yes, of course, yes, because in an infinite group, each element has a finite depth. So if you are in an infinite group, if you multiply by enough generators, you are going to reach a larger sphere. So in particular, if you have only finitely many dead ends, you're going to have uniformly bounded depth. So yeah, you need infinite many of them to have for any positive integer depth n.
But you don't have the other equation.
No, for example, you can in fact you can easily get examples of even hyperbolic groups which have positive density of dead ends of bounded ends, of course, meaning that if you take a ball of radius n, asymptotically you have like a proportion of like 1 over, I think the number is like 1 over 2 to the 12 elements that are going to be dead ends of bounded depth. But so these are like triangle groups. Reminding that we have this property. So it's not the same.
Okay, thank you.
Okay, are there questions on Zoom? No, we're okay. All right, let's thank the speaker one more time. Okay, so we have about 10 minutes until the next talk, which will be live streamed as the speaker is virtual.
Just a small remark for the organizers. It's great to see everybody better, even though I'm online today. So maybe it's good you stop recording again, and maybe you can start again, even in a minute, but better to split the talks